Hello, I'm Anna Mackay and this video is about confidence intervals. This first video is the theorem of confidence intervals and the second one will have examples in it. So I'm assuming you've watched the central limit theorem video and this rolls on from that, so I'm going to make some references to that. So a 95% confidence interval. Why 95%? Well, you might remember your standard deviations either side of the mean, and approximately one standard deviation either side is 68% of the data. So we say that that would be likely. 95% would be classed as very likely, and 3 standard deviations, 99.7%, would be almost certain. So 95% is a good compromise. It's one way of looking at it. Now, what's the purpose? Think back to that central limit theorem video where we talked about cans of drink, and then we looked at samples within that. So you could take a 6-pack or a carton with 24 cans. So we're looking at what does the value of the sample mean, x bar n, say about the true population mean. So thinking about the mean of the 24 cans in a carton, that taking the average there, if that's all that we could take, what could that tell us about the average volume in all of the cans? So we could only truly be sure what the true population mean would be of that if we collected data from the entire population, so every can ever produced, and that's usually not possible. But by taking one random sample from the population and determining its sample mean, it's possible to determine an interval within which, at some level of confidence, the true population mean will lie, and that's what a confidence interval tells us. So here's just some of the technicalities of it. Feel free to pause and have a read. I'm just going to move on from there. So with respect to the sample mean, starting to think about this confidence interval, so it's more likely than not that x bar n lies in the interval one standard deviation either side of the mean, with the standard deviation being this one, this population standard deviation divided by the square root of n, which is the sample size, so it could be 24 cans in that pack. 2 standard deviations would give you about 95%, and 3 would give you 99.7%. So as the sample size n increases, so if we had 6 cans, 24 cans, however big we want to go, our estimate for the accuracy of the sample mean gains precision, since the standard error decreases because we're dividing by the square root of a bigger number each time, so we're going to be getting more accurate the bigger that sample size. So for approximately 95% of samples, if we've got our x bar in the middle, now this is not the official formula, I'm going to show you how we get to the confidence interval formula. We're talking about 2 standard deviations either side of the population mean. But 95% is actually not exactly 2 standard deviations. So if we're going to have a 5% chance of being wrong, that would be the area at 2.5% either side of the distribution. Here's a picture. So 95%, looking at this one here, would mean that we have 2.5% either side, so 5% in total. So let's work out what that value is, this k value. We'd have to do an inverse normal calculation on that. So you could put your tail at the right, an area of 2.5%, this is a decimal, a standard deviation of 1 and a mean of 0 would give you a z-score of 1.96 here, or negative 1.96 on the left-hand side. So it's not quite 2, it's 1.96. So actually for a 95% interval, this is what it becomes. And this might take a while for you to get your head around, and this is why these videos are handy, because you could come back and watch this again another time. The confidence interval is actually this picture here. And because what that means is that the value of x bar n, so the mean of, so remember 24 cans in a pack there, the average volume of each can could lie at the upper end of a normal distribution or at the lower end. So what we mean is if the true population mean, the true average volume of each can is here, and our X bar 24 was bigger than that, so that could mean that there's cans with a little bit more volume than normal in them, then this is how it would sit. X bar N would be at the higher end, above the population mean, or it could be the other way around, that our average contained cans that had slightly less volume than others, and so it's on the lower end in comparison to what the true population mean would be. And as you can see, those two parts, those areas, would fit together and make this shape up there. And that's often where we visualize confidence intervals being. So moving on here, this is again what we're talking about here. Here is our nearly 2 standard deviations either side of the mean, so coming from one way and the other way. And so here is the formula that we're after. Another way to arrive at this is through rearranging the Z, the standard normal formula. Feel free to pause and have a think through this. I'll just summarize it quickly. So there is our formula for the standard normal. X bar, take mu over sigma. But in this case, the sigma is actually this over the square root of n. And we want between our Z scores of negative 1.96 and positive 1.96. Multiply by -1 and reverse the inequality. Simplify, so what I mean is multiply through by that denominator to take it to both ends of the interval, and add X bar N to each side, and then you're left with mu in the middle. So we're trying to work out what the population mean might be, an interval for it. Okay, so what this means is that we can be 95% confident, whatever that means, that the true population mean is between the two endpoints. So this is the 95% confidence interval for the population mean. That's officially what it's called. So 2 ways to get your head around what does that 95% confident mean. That's representing nearly 2 standard deviations away from the population mean either side. But also, if many samples of size N were taken, so imagine we've got 1 carton of 24 cans and we get the average volume of the 24 cans, and we take another group and another group and another group, that if you took 100 samples of size 24, in 95 of them, the true population mean would lie. I'll show you by a picture. So this does not represent the cans, but the concept's the same. In this situation, N is 60, and we have 100 samples. If we were to create a confidence interval, I know it's on its side, for each of those X bar N's, X bar N is in the middle of the sample each time, and the interval is worked out either side. If the true population mean is known, that's the red bar running through here. If you take that confidence interval, which is trying to predict for you where the population mean would lie between 2 endpoints, that in 95 out of 100 of them, the blue ones, that true mean, population mean, actually is. But in 5 out of 100, the red ones, it doesn't lie. So if you were to use that interval here, the one that's above, to predict what the population mean would be, you wouldn't actually be accurate. But you wouldn't know that because you've only taken 1 sample. And so your interval range would be fully above where you predicted. And that's going to happen. You can never be 100% confident. The only way you could be 100% confident of knowing what that population mean is to sample every single piece of data. And that's usually not practical. Okay, so the next video will be confidence intervals part 2 of 2 and doing some actual examples. Thank you.